Yo, Chuck.
Hey, what's going on YouTube? In this video, we're going to go over the Fibonacci sequence. I'm going to briefly explain what it is, and then we're going to go over an easy way to do the Fibonacci sequence, the recursive way, and then finally, we're going to do the recursive way with Memoization, which is an optimization technique that is much faster. So stay tuned and let's get started. Alright, so the Fibonacci sequence is just a sequence of numbers. You start with the first term, which is 0. You go to the next term, which is 1. And now I'm going to add these two terms together. So 0 plus 1 equals 1. And then 1 plus 1 equals 2. And then 1 plus 2 equals 3. 2 plus 3 equals 5, and so on. So you're just taking those initial two terms, adding them together to get the next term, and then you're repeating the process indefinitely. This will quickly spiral out of control and the numbers will get huge. It's worth mentioning that the Fibonacci sequence is a sequence and not to be confused with a series. A series would be if I was to sum a bunch of these numbers. That's not going to be the case in this video. We're going to go over how to find a specific Fibonacci number at an index. So if I said I'm going to call a function Fibonacci with the index of 5, so I would start at 0, which would be index 0, and then I go 1, 2, 3, 4, 5, so that would be 5, and I would expect to return the numeric value of 5. So that's an important distinction to make. And just to prove to you that 0 is in fact the first term, I did a quick Google search and you can see 0 is in fact the first Fibonacci sequence number. Why is that important? Because frequently on these algorithm websites, people will mistakenly say 1 is the first term and then 1 is the second term, and then it goes 2, 3, 5, and 8. This is incorrect. Do not do this. 0 is technically the first term. Okay, so now that we've made that distinction, let's go on and actually code some stuff. Okay, so the first way we're going to do it is the easy way that everybody knows. So I'm going to come in and make a function called Fibonacci. It's going to take a index value, and what I'm going to do first is I'm going to make some variables. I'm going to say number 1 and set that equal to 0. And then I'll make another variable called number 2 and I'll set that equal to 1. It's worth mentioning here that frequently on websites you'll see the parameter of index will actually be called like number. That's kind of misleading because you're actually searching for an index or you're searching for a value at a specific index. So to just make things more clear, I'm calling this parameter index. But if you were to go on like another website and like look for a solution code, it might be called number. Okay, so we've got number 1, number 2. Also, I'm going to make a variable called next, which I'll initially set to null. And that is going to be the next term. So I'm going to add number 1 and number 2 to give me the next value. Now I'm going to do a while loop, and I'm going to say while index is greater than 0, I'm going to do stuff inside this while loop. So firstly, I'm going to decrement the index value, and then I'm going to set the next variable equal to n1 plus n2. That is going to capture the next term in our sequence. So if 0 is the first term and then 1 is the second term, the next, which should be equal to 1, right? And so on. Then I'm going to update the value of number 1 to number 2, and then number 2 to be number next. And then I'm going to just return the value of number 1. So if I run this guy here, let's put in an index such as 3, okay? I'll open up my terminal, and I get 2. That seems about right, but let's double check. So I start at index 0, 1, 2, 3. So that looks right because 2 is at index 3. Let me write this out a couple more times so we get a little more values. Okay, let's grab an index, let's say at 5. So index 5 is 5, right? Because I start at 0, 1, 2, 3, 4, 5. So this should return 5. If I run it, it does. What about index 7? That should return 13, right? And it does. Excellent. So this is the first way, and this is like the most basic way that people will use. Again, I'm using index as a parameter. Typically, you'll just see this called num or number. But that is the easy way, and now that we've done the easy way, I want to show you the recursive way. Okay, now we're going to do the Fibonacci sequence with a recursion, which, if you recall, recursion is just a function that calls itself until it doesn't. It is basically another way to loop through data. So we can loop through those indices in a certain way to get to what we want and return the correct value. So let's do that now. The first thing I'm going to do is set up an edge case. So I'll say if index equals 0 or index equals 1, return index. So this is going to be the base case that will cancel our recursive call if our Fibonacci function is equal to 0 or 1. And if that is not the case, we're going to return Fibonacci. We're going to put in our index, we're going to subtract 1, and then we're going to add Fibonacci index minus 2. So this is kind of the inverse way of what we were doing before, where we started with the while loop and then we kind of like built up from the ground up. This is like the opposite, where you're starting from the top level down and then you're adding values. And notice here that I'm saying if index equals 0 or index equals 1, return index. This will give you an accurate representation of what you're looking for. A lot of times you'll see on websites they'll do this. They'll say if index is less than or equal to 1, return 1, which will this is incorrect because you're going to end up skipping that 0 term. This logic right here again assumes the first terms are 1 and 1, which I explained in the other video or the other lecture that that's not the case. So this is incorrect. Use this logic up here, and when we make our recursive call, it's starting from the top down. Now I can explain this better with a visual representation. So if we hop over here, we can see we start with the initial call for Fibonacci at index 5. Remember, I'm subtracting 1 and 2 from this 5 number. So that's going to split off into 2 separate function calls, right? Right here we have Fibonacci 4. That's going to split off into 2 function calls. And those function calls split off into other function calls. And then eventually you either hit a 1 or a 0, and that's when it kicks you out of the algorithm. So it'll just return that value. So if I did Fibonacci 5, I should return these values and then add them together, right? And then if I add Fibonacci 5, 1, 2, 3, 4, 5, is 5 at index 5? I'm looking down here, and it is. So it's kind of confusing, or it's hard to grasp, I think, what's exactly happening sometimes with recursive calls. But if you kind of like make a picture of it, you can see, oh, like when I make that first recursive call, it's going to call it twice. Then it's going to call this twice, and then it's going to kind of return a 1 or a 0, and then it's going to stop. This makes it easier to understand. So let's double check that if I put in 5, I should get 5 back, right? Let's see here. And I do. It's the same as before. If I put in an index, it should return the next number at that index, whatever I put in. So that looks good. That's a little more confusing than the first one. Now I want to show you how to do this recursively using Memoization, which is a speed optimization technique that we can use to go even faster. So let's try that. Okay, so for the Memoization piece, it's not much different than the recursive function we just made. I'm commenting out a original function we made and I'm just copying it and starting anew. You'll see why I did that later. But so first thing we're going to do is come in and then make a parameter called memo. I'm going to come down here and say memo equals memo or an object. So what this is basically saying is every time we make this recursive function call, memo is going to be either itself or an object. So if it already is instantiated as an object, it's just going to return the value of itself. But if it has not been instantiated as an object, it's going to become one on that first call. Okay, so pretty much the same code as before. I'm going to say if memo at index. So if memo at index exists, then I want to return memo at index. What this is essentially saying conceptually is I'm storing previous values of my Fibonacci numbers inside this data structure, which is an object called memo, and it's being stored at a specific index, which is going to be the number passed into it, and when it'll be subtracted here, and then if we have access to that number already, we're not going to perform the expensive calculations we were before. We're just going to grab that previously understood number. So I'm going to come into my return statement and adjust it a bit. Let's actually do an else to make it more clear. Okay, I'm going to put these bad boys in here, and then I'm going to pass in memo. Reason I'm passing in memo here is so that the value is stored each recursive call, which we want. Actually, let's do this. Let's just say result. And I'm going to return the result of my function calls. Because if you remember, when I call these functions at a specific index, if we go back to our visual diagram here, certain calls just become like number values, right? Like if I called Fibonacci 2, it's just going to equate to 1 plus 0, which is just 1. So if I know the value of Fibonacci 2 is 1, and I can store it in my memo object, then I can just pull that value up without having to continually and repeatedly do the same calculations. Likewise, if I eventually know that the value of Fibonacci at index 4 is, let's see, 0 plus 1 plus 1 plus 0 plus 1 is 3. Now I know that Fibonacci 4 is 3, therefore when I do this whole tree diagram of recursive calls, I can just be like, hey, Fibonacci 4 is now 3. And that will save us so much time. So let's go back to our code real quick. Okay, so I'm storing the result in that result variable. I can get rid of this right here. And I'm going to now store the result into our memo data structure we just made, which is an object. And I'll set that, should be index here because it's an index we are putting the value into. So let's say memo at index equals result, and then to actually get this to recursively call, I need to return the result, because recall, the result is actually the function calls of the Fibonacci function. So that's all there is to it for this memoization. Let's make sure it works first, okay? So if I did 6, that should be 8, right? And it is. Let's do number like, what if I do 0? What happens if I do 0? Notice that the base cases right here are still working, and then our memoization check, hey, if we've already done this work, why are we doing it a second time? Just return whatever is stored in that object called memo. Let's do one more. Let's do 7, which should be 13. Good. Okay. So how can you test this is actually working? Well, let's add a huge number, our huge index, to our function call and see how fast it goes. So I'm going to use a ridiculously big number like 30. And it instantly, notice how quick it instantly found the calculation for 30 at index 30. Very fast, right? Now, to prove to you how quick and slick this memoization is, I'm going to console log out our memo function, and I'm going to go back to the old recursive boy, right? So now if I do the same calculation, look what happens. It still goes pretty fast. Okay, well, let's try doing an even bigger number. 30 is not big enough, apparently. My computer's so fast. Let's try 40. 40 is pretty quick on the memoization front, right? Let's try 40 with the old guy. And here, you see it, you feel that? You feel how slow that was? That was pretty slow, right? Let's even jack it up even farther. I want to make my computer be in lots of pain. So just instantly how quick it does it with the memoization. All right, one more time. I'm really trying to bring this point home. Now, I don't know if this is going to crash my computer. Hopefully not. Yeah, there you go. So the old recursive call is having to do extra work, whereas the memoization is able to do the same thing, and it remembers previous values stored. And let's just remember this visualization. If we know the value of a specific function call already, why do the work a second time? And there you have it. That is the Fibonacci sequence. Be sure to like and subscribe this video, and I will see you in the next one.